Branches of science like acute biology, exobiology, or xenobiology delve into exploring potential life forms that might have originated and could exist beyond our planet. This extraterrestrial life could encompass anything from basic single-celled organisms to complex civilizations boasting expansive intellects, potentially surpassing humanity. In a previous segment, we employed various search methods, including the Drake equation, aimed at estimating the count of extraterrestrial civilizations within our galaxy, an intriguing concept we'll revisit in future discussions. However, for now, we're steering our focus within the bounds of our solar system, investigating what we've uncovered thus far regarding any form of life on the nearest planets and their moons. Let's embark on our journey, charting from the sun to the farthest reaches of our planetary system. Here's Mercury, our solar system's nearest planet to the sun. Its extreme temperature fluctuations, scorching on one side and freezing on the other, make it inhospitable for life as we know it. Although there might exist a thin oxygen layer, it's far too sparse to sustain any recognizable life forms. Perhaps deep beneath its surface lies a possibility, conceivably some form of life like subterranean organisms, though this remains highly improbable on this hostile planet. The reality is that the side facing the sun reaches unbearable heat, while the opposite side plunges into perpetual cold, rendering it incapable of supporting any form of life. It presents a dichotomy of a nightmarish inferno and eternal permafrost, making survival a daunting challenge. Next up is Venus, our solar system's second planet from the sun. In terms of size and structure, it bears resemblance to Earth, but with a critical divergence, an incredibly scorching surface capable of liquefying lead. It's a place where no life as we know it could survive, burdened by a crushing atmosphere and characterized by volcanic activity. Initially, Venus's geological evolution might have mirrored Earth's, potentially hosting oceans and offering the prospect of surface life. However, divergent trajectories set these two planets apart dramatically. The unchecked greenhouse effect likely evaporated Venus's oceans, transforming it into a blazing inferno, making it the hottest world within our solar system. This fiery scenario paints a stark contrast to the more temperate Earth group planets. Despite the extreme and inhospitable conditions, researchers haven't discounted the significance of Venus. Recently, traces of phosphine were detected at an altitude of 50 to 60 kilometers, albeit in small concentrations, slightly surpassing methane levels found on Mars. This discovery has sparked intrigue due to its potential implications. Phosphine, chemically reactive, ultimately breaks down into pure phosphorus and hydrogen under elevated conditions. Furthermore, within Venus's clouds, phosphorus should naturally descend without the presence of hydrogen. This contradicts continuous observations of phosphine from Earth's telescopes. On Earth, anaerobic bacteria historically generated phosphine. The question arises, why would such bacteria exist in Venus's atmosphere? Some speculate on the prospect of advanced civilizations preceding us initiating such processes. However, this notion remains highly improbable. While non-biogenic pathways theoretically allow for phosphine formation, such as volcanic emissions, its relevance to life remains uncertain. Nevertheless, this discovery on Venus stands as a captivating and thought-provoking find. Meanwhile, we're heading for Mars, another celestial body with the potential for life in the habitable zone of a star like Venus and Earth. This red planet narrates a tale akin to Venus, albeit on the opposite end of the temperature spectrum. Data from orbiters and rovers on Mars's surface corroborate its past as a world potentially humid with rivers, lakes, and potentially oceans. However, the relentless assault of solar winds and radiation eroded most of its atmosphere, and the planet's minimal active core ceased generating a protective magnetic shield. Consequently, Mars transformed into an inhospitable, frigid, and desiccated place, where survival requires subterranean refuge. The hope of discovering remnants like a space base or perhaps the remains of Martian life, whether buried beneath the surface or within the frozen polar caps, faces significant challenges. The scarcity of accessible water and the absence of tectonics, a process that recycles nutrients on Earth by shifting continents over eons, poses hurdles in the quest for Martian life. Detection of methane in the Martian atmosphere offers clues. On Earth, methane replenishment occurs through the metabolic action of diverse life forms or through reactions between water and rock. Yet, the potential for microbial life lurking beneath the surface remains a plausible hypothesis that should not be disregarded. Notably, the rover Curiosity detected intriguing organic compounds, including aliphatic and aromatic compounds, along with derivatives of the TE, tricarboxylic acid cycle, containing 4 carbon atoms and 1 oxygen. This discovery holds significance as similar molecules on Earth are associated with biogenic origins found in coal, crude oil, and products generated by microbes and fungi. Nevertheless, the possibility remains that these Martian compounds could be abiotic, formed via geochemical processes. The anticipation for a future exo-Mars mission to shed light on these mysteries is palpable. The pivotal tool aboard the rover, a drill capable of excavating to depths of up to 2 meters, promises to unravel these enigmas. However, its launch, initially slated for 2024, has faced postponements. Continuing our exploration in pursuit of life, we approach the grandeur of the solar system's colossal giants: Jupiter, Saturn, Uranus, and Neptune, each accompanied by chains of moons that could be deemed nearly self-contained solar systems. Within these satellites lie promising prospects for habitable worlds, such as Europa, a moon of Jupiter, covered in an icy shell that appears devoid of life at first glance. Yet beneath this frozen exterior, space probes have unearthed evidence revealing vast liquid oceans on Jupiter's other 2 moons, Ganymede and Callisto, potentially sandwiched between layers of ice, which somewhat diminishes the likelihood of life. However, Europa stands apart due to its significant contact between the liquid subsurface ocean and the rocky interior. This interaction allows mineral compounds to leach into the water, potentially serving as a resource for life, perhaps even hosting alien creatures akin to killer whales. Additionally, traces of hydrogen peroxide, crucial for methanogenesis, the creation of methane by anaerobic archaea, have been detected, indicating further potential for life. For life to thrive, resources like peroxide are essential, but thermal energy is also crucial. Europa likely possesses this thermal energy due to the inner layers shifting and deforming under the gravitational influence, leading to friction and heat generation. This process warms the moon's mantle and subsequently heats the underlying ocean layers, making Europa one of the warmest places where life could flourish. Moreover, the likelihood of oxygen formation on Europa's surface, influenced by the solar wind and geological processes, suggests a potential for oxygen entering the ocean. However, the concentration of oxygen within the water remains undetermined. Regarding potential life forms, it's theorized that the trophic chain's foundation would comprise chemotrophic bacteria forming organic sediment layers on the ocean floor. Other organisms would feed on these sediments, analogous to herbivores or, in a sense, akin to vegans in Earth's ecosystems. These creatures forming the trophic chain sustain and interact within this intriguing environment. Among Saturn's satellites lies Enceladus, diminutive yet potentially harboring habitable conditions. Beneath its icy exterior, This moon conceals a liquid ocean, a unique feature in our solar system. Unlike other celestial bodies, Enceladus provides accessible samples of its ocean without the need for extensive excavation or drilling. The Cassini spacecraft once ventured through the plume emanating from this underground ocean, although it didn't gather any visible algae. Nonetheless, it uncovered pivotal evidence, including complex organic salt molecules akin to those found in Earth's oceans, silicate nanograins, and signs of hydrothermal activity. Gases like hydrogen and methane detected in the plume hint at the presence of sufficient energy sources that could sustain life, making Enceladus an intriguing target despite its size and lower gravity compared to Earth. On the other hand, Titan, another moon of Saturn, bears some resemblance to our own planet. Nitrogen, like in Earth's atmosphere, dominates Titan's atmosphere. However, Titan stands unique as the sole entity in the solar system boasting rain lakes and rivers, albeit composed of methane and ethane hydrocarbons, rendering conventional bathing suits futile. Beneath its surface lies another water ocean, though far deeper, and its potential connection to the surface remains unknown. If this ocean interacts with surface chemistry, it could potentially foster life. However, in its absence, there exists the possibility of an entirely different chemical composition and reaction dynamics fueling life forms, unexplored and exotic, yet to be comprehended. The extreme cold prevailing on Titan's surface significantly retards chemical processes, if not halting them altogether, creating a slow-paced environment for chemical reactions. Despite these challenges, the mysteries of Enceladus and Titan continue to entice scientists, offering insights into potential forms of life and their sustaining conditions beyond Earth. Currently, there's only one place where life is definitively confirmed: our very own home, Earth. Yet, the more we delve into our cosmic neighborhood, the more unexpected discoveries await us. This journey of exploration across planets and their moons within our solar system promises an array of surprises. As we push further, exploring even the outermost edges of our system, and who knows, perhaps even venturing far beyond.